Hi, today we're going to look at Atcoder Beginner Contest 373, problems A to E. So let's look at problem A. For this problem, we're given 12 strings consisting of lowercase English letters, and we're supposed to count how many of these strings satisfy that the length of the string is equal to I. So for this problem, we can just directly check each of these strings, whether they're equal to I. Let's look at the code for this problem. We first input these strings, and then we just check if the length of the string is equal to I. If it is, we increment the answer, and then lastly, we just see out the answer. Let's look at problem B next. So for this problem, we're given a keyboard that is a permutation of the 26 alphabets. So for this problem, we're supposed to input the alphabets in order. Initially, our finger is at the location of A, and we're supposed to move our finger to B, C, D, and so on. And we're asked to calculate the distance that our finger needs to travel to type out all the alphabets. For this problem, we can record the index corresponding to each letter from A to Z. So we can store this in a map and record the index corresponding to each character. So for example, we can look at sample input 2. So for this example, SM would correspond to 0, and SG would correspond to 1, SJ would correspond to 2, and so on. And so the answer would simply be the distance between A and B and B and C, C and D, and so on. Let's look at the code for this problem. So first, we just input the string S, and for each character in S, we store in a map that maps the character to the integer of where the character is located in the string. So afterwards, we calculate the distance between A and B, B and C, C and D, and so on, to find the minimum distance that we need to move. So for this part, we just record what the previous index is and just add the absolute value of that with the current index we're in. And afterwards, we just print out the answer. Let's look at problem C. So for this problem, we're given two integer sequences A and B, each of length n. And so we're supposed to find integers I and j to attempt to maximize the value of AI plus bj. So we notice that the maximum value of AI plus bj is simply the maximum value in A plus the maximum value in B. So the maximum value has nothing to do with each other. So the time complexity is simply O(n) if we look at the maximum value in A and find the maximum value in B. So for example, for this input, the maximum value in A is simply 15, and the maximum value in B is 18. So the answer would just be 15 plus 18. Let's look at the code for this problem. So for this problem, we simply need to find the maximum value in A, which is this part, and then find the maximum value of B. And then the answer would just be the sum of the two. Let's look at problem D. For this problem, we're given a directed graph with n vertices and m edges. Each edge is from U to V and has a weight of W. And we're supposed to find an assignment for each of the vertices so that the number on the vertices xv minus xu is equal to W. What this means is that, for example, for sample 1, if vertex 1 is assigned a number 3, vertex 2 would have to be 5 because the edge between 1 and 2 has a value of 2. And vertex 3 would have to be a value of 2 because 2 plus 3 equals 5 and 3 minus 1 equals 2, which satisfies all the edge constraints. So we notice that there are multiple answers for this problem. And so for example, this solution, the x is equal to 3, 5, 2. But we notice that an assignment that is equal to 2, 4, 1 will also work. So would 1, 3, 0, and so on. So we notice that only the relative order of the vertices are important. So like the difference between each edge is important, not what the edge values actually are. So we notice that we can simply assign a value to one of the vertices because once one of the vertices in the connected component is determined, the rest of the values of that component are fixed. However, there can also be many components. For example, sample input 2. The entire graph is not connected, but is instead split into these two groups. So for each of the connected components, we can just determine one of the values. And then we can find the values for the other vertices. So this algorithm would be DFS. So we can simply do a DFS on each of the components and find the values after we assign it to one vertex. Let's look at the code for this problem. So first, we just construct a graph that points from U to V with weight W and back from V to U with weight negative W. So we keep track of a visited array that is Boolean to know whether the vertex has been visited yet. So if the vertex hasn't been visited yet, we just do a DFS. So for this part, we do a DFS with the starting node assigned a value of 0 because the global variables here are automatically assigned values of 0. So afterwards, if the vertex V here is not visited, the answer V would be changed to answer U plus W, which is just the edge weight of this edge. And the vertices would be marked as visited, so we would visit the entire component. So afterwards, we can just simply print out the answer for each of the vertices. Let's look at problem E. For this problem, there's an election with n candidates, each numbered from 1 to n. There are k votes, and some of the votes have already been counted. So candidate I has already received AI votes, and we're asked to determine a integer x, the amount of the amount that the votes increase for each of the candidates, so that even if the other votes are cast, they still win the election. And in this problem, for a candidate to win an election, the number of candidates that have more votes than them needs to be less than n. So, for instance, let's look at sample input 1. So for this sample, there are 5 candidates and m is equal to 2. The total number of votes is 16. But in this case, there are already 14 votes casted. So for candidate 1, we will need an increase of 2 votes for them to be ensured to be the winner. So because 14 votes are already casted and there are only 16 votes in total, so there are 2 votes left. However, if 1 vote additionally is given to candidate 1, candidate 3 can receive the other votes because there are 2 votes left. And then candidate 3 and candidate 5 will both have votes that are greater than candidate 1. So candidate 1 will not win in this case. So candidate 1 would need an additional of 2 votes for them to be guaranteed the winner. And for candidate 2, it's impossible for candidate 2 to win with only 2 votes left, because even if both of the votes are added to candidate 2, candidate 2 would only have a value of 3, and candidate 3 and candidate 5 have a value of 4 and 5, so they're both greater than candidate 3. So it's impossible for candidate 2 to win in this case. And afterwards, for candidate 3, they only need an addition of 1 vote to win, because the other vote could be given to candidate 5 or candidate 1 and would also make no effect, because candidate 3 would still be the second greatest. Let's look at the algorithm for this problem. So we notice that we need to compute the answer for all of the candidates, which takes linear time. And so we can't directly loop through all of the values that they need to increase by, because that would take another k. So the time complexity would become O and k, which is unacceptable because k is as large as 10 to the 12th. And so when we see a number this large, it gives us a hint that we can do binary search on x, because there will only be one best value for x that satisfies the answer. So we can do binary search, and for the check function, we would need to check like whether a specific value of increase for a candidate would work. So for example, let's look at candidate 1 in this case. If x is equal to 1, and in this case m is equal to 2, and so we would need to check if a increase of 1 is enough for the candidate 1 to win. So we would need to count the additional votes that are needed for n candidates to have votes greater than candidate 1. So in this case, there are 16 votes, and 14 votes are already cast. So there are a remaining of 2 votes. And if we already give candidate I 1 vote, then there is only a remaining of 1 vote. So we will want to give the remaining 1 vote to the largest candidates, which are candidate 3 and candidate 5. Because the reason we will want to give to the largest candidates is that this would make them be greater than candidate 1 as a lesser value, because if we give the votes to candidate 4, then they would need another additional 4 votes for them to be greater than candidate 1. So it would be best to give the votes to the largest candidates. So in this case, the additional votes that we would need is only 1, because after adding 1 to candidate 1, the value is equal to 4, and we would need 2 5s for the other 2 candidates. And so for candidate 3, they would need another additional 1, and candidate 5 is already 5, so they will only need 0, and the result is 1. And so in the check function, we can check if the number of additional votes that we need is less than or equal to the remaining votes. So in this case, we have a remaining vote of 1 and the additional vote of 1. So this means that with the remaining votes, it is still possible for the other candidates to have m candidates that have values greater than candidate 1. So in this case, this would not work for a increase of 1. And in the other case where the additional votes are greater than the remaining votes, this means that even with all the remaining votes cast, it is still impossible for m candidates to have values greater than candidate 1. So this would work. And however, we notice that if we need to calculate the value for the remaining candidates, like for m candidates that are greater than the candidate we're checking, this would take another m time, which wouldn't suffice. So in this case, we can use prefix sum after we sort the votes that are given. So for example 1, if we sort the votes that are already cast, we would get 1 1 3 4 5. And so because we would always give the votes to the larger candidates, so we will always give the votes to these candidates. And we can calculate the value of this range, like the sum of this range, easily using a prefix sum. So the additional votes would simply be the total votes needed for this range minus the votes that are already, the votes that they already got. So we can do the sum of range, which can be calculated with a prefix sum. Let's look at the code for this problem. So in the first part, we just input the values of A, which are the votes that are already cast. So, and we calculate the sum because we need to find the votes that are remaining. And we need to keep track of the order because later we will need to sort the array from increasing values to get, so we could do prefix sum. And so we can define our own compare function for the sort too. And in this case, we sort it in increasing order. And so we sort order based on the values of A, so we can still have the indexes. And afterwards, this part is just computing the prefix sum. And this is important because for cases that n is equal to m, all the candidates wouldn't need any increase because no matter what value their votes are, they will always be the winner because there can't be m candidates that are greater than them. And afterwards, this part is just the binary search. So we first do a binary search on the number, on the votes, the amount of increase for the votes, and we check if this amount of increase is suffice for the to guarantee that the candidate wins. So for the check function, we need to do a lower bound to find the value, the index where the value is less than the current value, less than or equal to the current value, because if the values are already greater than our new value, like after the candidate is given a specific amount of votes, then we wouldn't need to increase those votes. So if they're already greater than m candidates that are greater than this candidate I, then we return false because then this means that this amount of increase wouldn't work. And afterwards, we also need to be careful to check if the candidate I is in the last m, because we can't count candidate I as like one of the m candidates that are greater than itself. So if candidate I is already included in the last m, then we would need to subtract 1 from the range and also subtract the value for that candidate. Otherwise, we will only need to check the values for the last m candidates. And so after we compute the additional votes needed, we need to check if the additional votes is less than or equal to the remaining votes that we have. Then this is return false because we will have a way to give out the votes so that there are m candidates greater than I. So otherwise we return true. And afterwards, we just need to check if it's possible, like in the given votes that we have, whether it's possible to guarantee that candidate I wins. So if not, we will assign the answer to -1. And in this case, because we already stored the order, like just the index after we sorted it for each of the candidates, we can assign the answer to -1. And otherwise, we can just assign the answer to our result after doing binary search. And lastly, we just input the answers. Print out the answers.